Good morning, everyone. Cool. Hey, hello, everyone. So super quickly, before we get started, as many of you know, we have a banquet tonight. Ooh. The banquet officially starts at 6:30, but if you want to start showing up at 6, that would be awesome. The food will probably be available early. That's how I get the students there early, just so you know the food's early. There's also, while I'm drunk with power up here, I'm also just going to announce that there is an unofficial CEDAR after party occurring after the reception at Lucille. It's a bar on Rainy Street. If you want to get any help getting there, feel free to find me. Other things as well. Actually, I think that's all the announcements I have to make for the morning. So we'll get right into it. So our first thing that we're going to be talking about today is an early career science highlight. We have Wang from University of Colorado Boulder, and they're going to be talking about ionosphere-TEC and disturbances observation using Spaceborne GNSS reflected signal measurements. So come on up here. Thank you.
Let me test this. Okay. Hello, everyone. Good morning. I'm Wang from CU Boulder, and it's a great pleasure to present here, and I really appreciate this opportunity. And the work is about using the reflection signal received by the LEO satellite to observe the ionosphere. And I would like to especially acknowledge Professor Jay Morton, who was my PhD advisor just half a year ago. And sorry, how to move forward? Okay. So here's an illustration of this concept, and we believe this approach can provide a potential new data source for the ionosphere observation. And here we assume a LEO satellite, and it receives, just like all other LEO satellites, it receives the direct signal from above the orbit using the navigation receivers. But we focus on the signal that is reflected from the Earth's surface and picked up by the LEO satellite. And the great thing about this approach is that it provides the observation for regions that we usually don't have any measurement, or we have just very few measurements, such as the polar regions or some ocean regions. And there's also some challenge dealing with this kind of measurement, because as shown here, the contribution from this refraction signal consists of this incidence ray and this reflection ray. So it's difficult to separate. It's not possible to separate these two contributions. Just look at the single reflection signal. And I will talk more about this issue later. And more details about this is available from this paper at the bottom. And we have demonstrated this approach with real data from Spire's CubeSats. And these CubeSats were designed for radiocultation and adjusted to process this reflection signal. So there are quite a few problems with these kind of receivers on board these CubeSats, but it's pretty good to have this opportunity to demonstrate this approach using these real measurements. For the rest of this presentation, I will start with a discussion on how this GNSS observation can complement other GNSS observations. And here's one example of using the ground GNSS measurements to monitor ionosphere state. It is about over 5,000 ground GPS receivers monitoring the ionosphere during this St. Patrick's Day's geomagnetic storm. And it is doing a great job tracking the evolution of these ionosphere disturbances during this storm. But it's also pretty obvious that there are large areas of data gaps there, especially for the polar regions and in the ocean. And these results were generated by our previous former team member, Dr. Jenny Yang. And the other measurements people usually use of GNSS is from the radiocultation satellites. And these are great measurements from radiocultation and has the potential to provide a global coverage. But the problem with radiocultation is that the signal travels through the ionosphere over a pretty long distance, probably over 1,000 kilometers. Then the measurement is approximated at a single point called tangent point. So if it detects any ionosphere disturbance, we don't know where it actually is precisely. So there's definitely still need for new measurements to complement the global ionosphere observation, and I think we believe this reflection signal can make good contribution there. And here's the and now the primary target area for us using the reflection signal is the polar regions. And these two maps show the reflection tracks over just one day received by the global CubeSats. And the gray area under these tracks, they represent the sea ice extent. And the color of these tracks represent the signal-to-noise ratio, and only the high signal-to-noise ratio measurements can be used for the the ionosphere observation. And the objective is to observe the ionosphere, so we don't care where the signal was reflected. So it's more important to look at the ionosphere coverage. So this shows the IPP tracks, which is a track of the piercing point in the ionosphere. So on the left shows the first IPP track, which is from the GPS satellite to the Earth's surface. And the plot on the right shows the IPP2 track, which is a signal reflected from the Earth's surface and goes to the LEO satellite. So these two, as just mentioned, they can be separated by a pretty long distance, several hundred to 1,000 kilometers. And the left shows IPP coverage, and on the right shows IPP2 coverage. You can see that over the polar caps, there is pretty high density observation, and the coverage goes down to about 45-degree latitude. And here's a similar pose for the Antarctica. So it still also have pretty high density coverage. But these measurements are from these CubeSats over one day, and we hope that we can have such measurements over just maybe 15 minutes. Then it's pretty easy. We can have a high resolution and high cadence TC map for the high latitude regions. And here are some illustrations of coherent versus non-coherent refractions. On the left is always coherent refractions. It occurs for the smooth surface, and the surface smoothness is related to the signal wavelengths and the elevation angle of that refraction. And overall, the sea ice is a good refractor to have coherent refractions. And the conservative estimation is that about 50% of the refraction over sea ice is coherent. And in addition to sea ice, we also look at the refraction from calm ocean surface. And the bottom plot here, sorry, how can I go back? No, it's just okay, it's a delay, thank you. This purple, this area, by the purple color, it represents the area that we usually have low wind speed. Here we use 7 meters per second, and more recently we are using 5 meters per second wind speed. So in these regions, it's very likely we can also have this kind of coherent refraction to provide the carrier phase measurement to observe the TEC. So this region can also provide the ionosphere observation for these low latitude regions. And the next part is about data processing and validation. And here's one example. So the signal is reflected over this Carrier Sea, which is part of the Arctic Ocean. And this event just within 3 minutes. And the refraction track is over 1,000 kilometers. And even if we are already just looking at the coherent refraction signal, then the coherent refractions, they have various level of coherence. And usually we are dealing with these kind of measurements is like these bottom two lines. The carrier phase measurements, they have very large noise, and this here show a lot of carrier phase cycle slips. It is due to the large noise in signal measurements and outliers. And we have to deal with this issue before using these measurements for the TC retrieval. And this issue has already been addressed by developing this ScanF method, which is the simultaneous cycle slip and noise filtering method the details are available in the paper at the bottom. And the bottom plot shows the difference between the L1 and L2 carrier phase. So it's pretty straightforward to use this phase measurement difference to retrieve the TEC. And after reconstructing the carrier phase measurements using the scanf method, then we can retrieve the slant TEC along the signal refraction path, which is a red curve. And we also compared it with the global ionosphere TEC map from IGS service. And we see obvious consistent trend between the two of them. But from the refraction signal, we see very high precision and high resolution variation of the TEC in the ionosphere. And these represent the real electron variations in the ionosphere, and we can easily demonstrate it by looking at the altimetry results, which is the next plot. So the green line here represents the model of the ocean surface. Here is a sea ice surface. It's based on the mean sea surface model and the ocean tide model. So over such a long distance, this model is pretty reliable. And here we compare the performance of using the signal estimated ionosphere TEC and the GIM-derived TEC to correct the ionosphere error for the altimetry. And we can see that it's pretty obvious using the estimated TEC with that kind of variations, we get altimetry results agree with the model within 10 centimeters. And we use a GIM, that variation can be up to 1 meter. And another use of these altimetry results is that we use this to demonstrate that the cycle slips have all been successfully corrected. If there's any uncorrected cycle slip, that will cause error in the TEC estimation, and it will show in these altimetry results as a sudden jump of a few decimeters. And in addition to the total electron content, we also look at the disturbances. And a few indices have been used for ground measurements, such as ROTI, rate of TEC index, the S4 index, and the sigma phi. And here we just look at the ROTI. And we have selected two sets of data. One is over during a quiet ionosphere, and the other is during storm time. So we calculate the ROTI for each set of data we selected, and these are all randomly selected for the time periods. And we see obvious sensitivity of using this ROTI of the refraction signal to sense the disturbances in the ionosphere. And I also have some very preliminary but very interesting results to share. And the first one is the observation of the ionosphere patches from the refraction signal, which is the black line here. And on the left is a magical vertical TEC map. The resolution is 1 degree by 1 degree. And the bottom one, this red line is IPP1 track, is the incidence rate. And we can see obvious consistency in the trend for this IPP1 track with the refraction signal. This is an ideal situation that we can use a refraction signal to augment the TEC observation. If we take difference between this black and red line, I think that will be a more accurate estimation of the TEC for that purple line here. There we have very sparse observation, and the mapping results doesn't seem to be very accurate. And the other example is ionosphere trough observation. It's just pretty cool to see this kind of large variation up to 25 TEC units. And there are two tracks. They are recorded, just one is 24 minutes after the other, and they see very similar magnitude of the variation and similar trends. And we can also see some TEC variation that is probably due to some wave propagated into the ionosphere. It is about 10 hours after the Tonga eruption, so it has to be related to some kind of wave related to the Tonga eruption. So this to be analyzed with ground measurements and other non-GNSS measurements to distinguish what it really represents. And here's a quick summary that we discovered and demonstrated this approach as a potential new data source. And it's pretty challenging to separate this TC contribution from instance and refraction rates without sufficient observation. And this data from Spire Global's data products through NASA's commercial small set data acquisition program, but that is just some raw data from their onboard receivers. So pretty complicated further data processing is required to get the TC observation. And we are working on the further data processing. And yeah, we acknowledge the support from NOAA, NASA, and DARPA through multiple projects. And these are relative publications. Please feel free to request any of the papers from us. Thank you.
Sorry. And I think we have time for one quick question. Okay, for the sake of time, we'll move on then. Up yet? Next. Oh, was there one? Oh, David? Yeah, David Themens? Oh.
So like, this is a really cool data set for high latitudes, right? I operate a high latitude data assimilation system for the Department of National Defense, and this would be a really, really excellent data set for us to assimilate. Even ignoring the separation between the incident and reflected rays, just assimilating the whole thing. I'd love to talk to you later, maybe.
Sure.
Yeah, sorry.
Thank you.
Thanks.
Okay, good morning. So the CEDAR Distinguished Lecturer recognizes a colleague who has helped to shape the CEDAR program through research and service. And so it's my great pleasure to introduce this year's distinguished lecturer, Dr. Anthea Costa. We all know Anthea, but quick summary of her many accomplishments and service to our community. So Anthea is a principal research scientist at the MIT Haystack Observatory, where she also serves as the assistant director. And Anthea's seminal contributions to our profession have truly enabled our community, the CEDAR community, to conduct ionospheric research at spatiotemporal scales that we simply couldn't do before, so that were not achievable. Based on the first real-time ionospheric GPS monitoring system she and her co-workers at Lincoln Lab developed back in '91, her pioneering work on introducing and relating GPS measurements to fundamental research has really led our community to now employ GNSS as a viable and, as I think, a truly information-rich sensor for ionospheric remote sensing and space weather monitoring. Anthea led the development of the GNSS tag database in Madrigal, and probably most of people in this room and many generations before have used this data, and I ask Phil Erickson, and in 21 alone, more than 300 different users downloaded almost 250,000 of different GNSS data products from the database, which I think really shows the impact of this unique data set. Anthea also has extensively served our community over many years on actually quite a few really impactful committees and in different capacities, and not to the least on committees from the national academies, and she's still the active co-chair of LPAC, which is a really important program to put our science into the LWS program, which I think was quite often a challenge to do. That's so we are truly grateful for that. And overall, I mean, Anthea is a truly tireless voice for our community. She advocates for our community, for CEDAR instrumentation on all the different committees to the federal agencies and others. And also, Anthea is really one of the key voices who advocates for the upcoming GDC and dynamic missions to proceed with these missions here. And we heard over the week already how important that is to continue making this, this case here. So apart from several books that Anthea edited or co-edited, she has also published over 170 papers. And I looked up the citations there, so they were cited over 7,000 times, so it's a truly impactful scientific work. And now I think I stole enough of your time, Anthea, so you have truly shaped our field, and we are very much looking forward to your distinguished lecture.
I have notes, so I don't forget everything I want to say, but first, I want to thank the CEDAR Steering Committee for this honor. I was and am especially humbled when you look back at all the people who have done this, and it's like, oh my gosh, me? I don't even fit with these people. But it's especially meaningful for me because I graduated from the University of Texas here in 1975, so not quite 50 years ago, although Bob McCoy did point out to me that as a freshman, that's over. I was here in 1971, that's more than 50 years ago. So anyway, I graduated with a liberal arts degree. It was from an honors program, and I had a specialty, so I was already kind of an oddball. I specialized in mathematics, and you're going to say, well, why didn't I do physics? Why didn't I do engineering? Well, at that time, in 1970s, early, although the university was 40,000 students, there were only 4 women, 4, majoring in electrical engineering. I actually tended to do the highest scores in the engineering math courses, but every time I kind of talked to people, they would go, oh, engineering, it's too hard. It's not a field for women. So I'm very glad that times have changed, but I just want to point that out, that 50 years ago, things were different. Now, luckily for me, I went back to Houston, and I started working at an oil company, and within 3 months, I was taking physics courses at night at the University of Houston. And for the next 2 years, I took as many courses as I could in physics and math, additional math courses. And Rice University accepted me with a deficiency, I might add, in physics. But they did accept me for the graduate program, and from that point, my career started. So the other thing I want to say is science is never, ever done in a vacuum. And so I want to thank a lot of people, but the entire staff at Haystack, but in particular those here. There's Phil Erickson, Larissa Goncharenko, Shangrong Zhang. I think Urcha is not here, but he was here earlier. Also, John Foster, who is now retired, but certainly he led our group and encouraged me early on, and I'm very grateful. And there's one colleague, Dave Tettenbaum, who many people may not remember, but he was my age, and he passed away in the late 1990s. But I remember sitting there, I was quite pregnant at the time, taking observations with the Millstone ISR and with our original GPS receiver, and we were there all hours of the night getting that data. So I've had a lot of support over the years. I'd also like to thank the many people I've collaborated with here in this room and those elsewhere, and if I don't mention your work in this talk, believe me, it was because I was trying to put far too much in this talk anyway. And I'm very, very grateful for all the GNSS signals that are out there. And yes, we should start using everything that we can. All right. With that, next slide. Oh, that's me, right? This one, right? Nope. Pointer. Oh. Yeah, okay. Forward. All right. So this is the only system science sort of idea you're going to get in this talk, but I just want to show you it really started taking off, I think, in the last decadal, and that's where we are actually starting to put all of the forces together and look at things as a whole. So we're looking at MI coupling, we're looking at lower atmosphere, upper atmosphere coupling. We're starting to put things together and trying to identify, the different, what have I done? Anyway, different forces. So that's what we're going to be talking about. Oh, this is different. Okay. then, so again, we're going to start again with a little bit of history. We're going to go back to mine. I was born, actually, before the first satellite was launched. And Sputnik, as you know, was launched in 1957. And at that time, if you think about it, so when I was born, there were 0 satellites. In 1957, there was 1, and it didn't stay up very long. As of September 1, 2021, there was 4,550 operational satellites. And I want to point out to everyone in this room, that number is going to go up exponentially within the next decade. So start paying attention. It's going to change. We're going to start having thousands of satellites up there, and I don't know what is going to be the result of it. I also grew up about 3 miles from, or 5 miles from Rice, where President Kennedy gave this talk. And for all of the younger people in this talk, if you haven't listened to it, listen to it. It was really phenomenal. I was not there, but I knew several people who were. And it was the talk of Houston at the time. I've given you the YouTube link, but I will read this. It says, "Why some say the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? Why does Rice play Texas?" We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. And I just think this was probably the most motivational presidential talk I've ever heard. Now, I am biased because I'm a science nerd, but it's worth listening to. So I was trying to look for photographs what Austin looked like back 50 years ago. And it was a completely different city, but it was always charming. And as you can see, the area around here didn't look anything at all what it did there. But what I wanted to point out was calculators. I think they cost approximately, and I may have underestimated, 3 months of room and board. They were really expensive. I did not, although I had a math degree, I did not have a calculator until I was out working. Computer programs were all done on cards. All right. So then, as I said, luckily I started Rice, and I became an ionospheric physicist. I started learning about the different regions of the ionosphere, about radio wave propagation, about the different layers, and I think this has become my career. And the radars I worked with for my PhD, there were 2. The big one, the Arecibo Observatory, which is sadly no longer with us, but I also worked with this 50 megahertz radar on the island of St. Croix. As you can see, it's pretty primitive. And we were using 9-track tapes, CalComp plotters, no personal computer, so I had to stay at Rice till past midnight most nights to get my work done. And most importantly, word processors were only coming in at the very end, so I was able to get my dissertation, at least the first draft, on a word processor, but I had to handwrite all the equations every time I did it, and that was such a pain. And I just want to point out, yes, there are cows in that field with my PhD radar. So I was looking at what science was done before pre-GPS, and actually quite a lot. But one thing we had close to Millstone actually was a Faraday rotation technique where they actually, I think, received data using Faraday rotation from the GOES-B satellite, and they were quite aware of these storms. So this is actually a storm where you see the storm enhancement, and then, by the way, this black is sort of the average TEC expected over the many days, and what you're seeing is that, yes, there's the storm time depletion following the initial enhancement. So all of this was studied before. Next slide. they were aware, and I'm pointing this out, DE2 satellite, because originally, as you know, GDC is going to be our next big mission. And here's what from DE2, which was nearly 40 years ago. And clearly, we were able to identify the trough here with this drop in NE from DE2 back in 1981. And there were certainly hints or measurements of what we call storm enhanced density with the Millstone Hill ISR. First in 1986, this is from a paper by John Foster. Here, it's still in black and white, and then a little bit later, by 1990, we had color printers. So you can see we had some evidence of structures during storm times at Millstone. Mind you, this is plotted in a different way. It's at one longitude bin, but these are different latitudes, and these are different magnetic times. So it's a different plot, but we did know about this feature. So now we're moving into the early GPS era, and this is the first GPS receiver I worked with. At that time, I was with Lincoln Laboratory, not Millstone Hill Incoherent Scatter. This was an advantage because this receiver in 1985 with the MIT discount cost $150,000, which was more than my first house. At that time, it could only track 4 satellites, but that was okay because there were only 4 satellites up there. And they would be visible, for 4 hours every day at the same time. So you could actually start to do positioning with those 4 satellites, but you had to be there at the right time when they were there. Now, I just want to remind the reason that we care about this is satellites transmit and receive radio signals that propagate through the atmosphere. And the 2 regions you have to be concerned about are the ionosphere and the troposphere. I obviously focus mainly on the ionosphere. And it goes back to what you probably learned in your elementary physics classes, refraction and dispersion. So the ionosphere basically both refracts and disperses the energy. So I want you to pay attention to this, because this is going to pay a lot. You're going to see this a lot going forward, and you're going to see it in here. This is the index of refraction, the Appletree-Hartree equation for the ionosphere. This is in its full glory. You don't really have to work with this full thing, but you should know about it. Actually, if you start for GPS or GNSS signals, you can ignore pretty much everything, but be aware that you are making approximations. You're left with actually n squared with 1 minus x. And that x is the ratio of the plasma frequency to the angular frequency. And if you actually go through all of the math, what happens is this. You can define total electron content, which is 10 to the 16th times electrons per meter square, and you have a range delay, and that means the additional amount of range that you're going to be measuring, because it's not, your wave is not traveling at the speed of light, and it's equal to 40.3, this is in MKS, divided by f squared times this integral of the electron density, which is TEC. So pretty simple. Now, this is just to give you a little sort of side thing. Luckily, one of the things you get to do is travel when you're a radio scientist. I got to go to Zambia to, I think it was an international ISWI group, so Solar Weather Initiative. Anyway, this is Livingston, Zambia. That's Victoria Falls. And we went there. I had no sleep because it takes like 24 hours to get there. But they said, oh, you have to go tonight because of the moon bow. You can see the moon. It's a full moon. So there we are, going out, breaking all sorts of rules, going to Victoria Falls. And indeed, we saw this beautiful bow right here with the over the water, and I was like, what is this? I study this. What is it? Why is it white? I don't understand it. And I actually went to sleep, and I think I dreamed about it. Next morning, I saw Jonathan Makela, and I don't know if you can see this very well, but he'd taken a photograph of it, and that's a rainbow. And the reason I couldn't see it was because that's the thing about your eyes, can only see in black and white at night. There's something about cones and rods and whatever. You cannot see it, but it really was a rainbow, and Jonathan's camera caught it. So it was pretty exciting, and I've always remembered this. So again, let's just give you a very brief, and I've talked about this so much, I just want to briefly cover it. GPS. So GPS was designed and never will be more than 32 satellites. They're in 6 orbital planes. There are 4 to 6 satellites in a plane. They're at 55 degrees inclination. They're in near circular orbit at about 20,000 kilometers, and they take 12 hours round trip. That's why I said you can see them twice a day. But the important thing is that each GPS satellite carries an atomic clock, an incredibly accurate time. And so they're transmitting both their position and their time. And with that, the receiver is able to get that and then calculate its own position. But in addition, because they knew the ionosphere was adding these delays, they designed it so that all of them are transmitting on at least 2, if not now 3 frequencies. The first satellites were launched in 1978, and it was fully operational in 1995, although they were saying in the Gulf War, the first one, they had 19 operational, and very soon after, it became sort of at least conditionally operational because they liked it so much. Now, back here, if you go, this just shows you how it works. You've got a receiver on the ground. Your receiver has a clock, but it's not an atomic clock. But you actually are tracking signals from up to 4 different satellites. You're supposed to be able to see 4 at any one time. You do a least squares solution. You solve for your position, and you solve for this bias, your time. So that's what you're doing. That's how it works. And as I said, the errors are all here, but the troposphere and the ionosphere are some of the biggest ones. The ionosphere can be directly solved with these 2 frequencies. The troposphere, you can do a pretty good job of modeling. And just again, this is what the measurement is. You actually look at the difference between the L1 and the L2, and with that, you can directly solve for TEC. So back in one of the papers I published in, I think it was 1992, where we did describe the real-time monitoring we were doing, this shows you the difference between the GPS group delay, which is very, very noisy, and the phase. And that was with our original receiver. And you can see at that time the ionosphere was much larger, because I don't think we've seen anything near that much at Millstone recently. We also, and I was happy to see this, I did some actually pretty good measurements. This is actually a comparison of GPS TEC with the Hamilton polarimeter, meaning we were getting the data from the Geospace satellite using Faraday rotation, and we were using the incoherent scatter. It's one satellite. You can see the incoherent scatter radar is underestimating the TEC, but remember, they're only measuring up to about 800 kilometers. We're measuring all the way out to 20,000 kilometers. So the difference was anticipated. It just says that there was that much more TEC above the height where Millstone could see. We also had a model that we had developed, and it compared pretty well with the standard bent model. That's an ionospheric model. We also, this is back in the 1990s, we're doing TID measurements. And basically, I was looking at this, we knew pretty much what was going on. Even then, we just couldn't see them. We knew that these were either caused or started in the auroral regions associated with geomagnetic disturbances or not, and they were probably due to atmospheric tides, tropospheric weather, volcanic explosions, earthquakes, rocket launches. All of that's true. And you can see back in 1991, I had a receiver. My friend Patricia Dougherty had one 25 miles away. We did a comparison, and you can see we saw, this is not on a high KP day, but we saw a very large TID come through. And looking at it now, I think some of these smaller ones are evidence of TIDs as well. And this actually was data from 1998, where, again, we were starting to work with larger groups of TEC from different sites. I was using 5 sites here, and you could see right there something's going on, a TID. And for the FAA, we actually did several months of comparisons between TEC units 25 miles apart, Lincoln Laboratory and Millstone. We had a KP equals 9 event, and we saw a huge number of TIDs during this time period when this storm came. So I would say if you think back to the 1990s, very few, if any, AGU CEDAR scientists used GPS TEC data. It's hard to believe, but at that time, nobody was doing it. And starting back in the 1990s, we started organizing yearly sessions at URSI UNC called GPS in the Ionosphere. We got people here from UTARL, from JPL, which was one of the leading groups, from AFRL, I was at Lincoln at the time, and as many other people as we could to start pushing forward. And the longer I was working with it, the more I thought this data needs to become part of atmospheric science. So it became a personal goal of mine to try and see that GPS data was more utilized by the atmospheric science community. And I would say I think that goal I have achieved. I also want to show you, this is Paul Kittner. He's no longer with us either, but he did some of the early scintillation work. This is in Peru. You can see they were in some kind of shed, but they were actually trying to measure scintillation in South America with our friends at INPE. Now, the other people I want to recognize, and this is something we really have to be grateful for, was that the International GNSS service was established, not by us, but by Geodesy, and that was actually for monitoring earthquakes and plate motion. And they actually got a lot of money to put out a lot of stations, but it was created in 1994. They were an early user of the internet, and again, if you think back to 1990, the internet was just coming online. And it turns out, I think, at the very beginning, our users were some of the most heavy in terms of use of the internet. IGS really stressed the importance of standardized products, freely accessible on the internet. For that, our community is grateful, but I just want, as we go forward, that is the most important thing they did. In the US, it's located at JPL, and it's really an interdisciplinary service of earth sciences and society. So, and I was talking to people at JPL last night. Basically, the very first TEC maps were made and developed back in go back? It takes a while, doesn't it? Yeah, well, you'll just have to trust me. When they started with IGS, they had only 20 stations worldwide, and they're now around 400 or 500. But even with those very few stations, they were able to produce a map of TEC over the U.S. back in 1993. Now, the problem was they were doing a lot of averaging, so they didn't have data from a lot of stations. They used models where they didn't have data. And that's the one thing we did differently, is that we only used data, but by the time we started doing it, there were more receivers, and we were using more than just the IGS receivers. So what happened in 2000? Very quickly, there was a large solar flare on July 14th. It was the biggest solar storm in 9 years, and it caused very, very large storm and ionospheric effects. KP was 9 for 3 consecutive time periods. I went to Phil Erickson at the time because I was still operating the GPS receiver at Lincoln, and I said, Phil, we lost data for 4 hours. What's happening? And he said, oh, well, we were that was a big storm. We were measuring huge westward ion velocity above Millstone Hill. Oh, by the way, that corresponds to electric fields. You probably had scintillation. So we started working more and more with the event. First, we just picked 4 receivers locally, and many of them had trouble. This is what that day looked like. But I was also operating a receiver in Florida. When I plotted that, we saw this, which nobody expected. In fact, people didn't even believe it because, it had been running much smaller, and then bang, what was going on in Florida? So we started grabbing all the data we could, and we put together our first map, and we saw the first SED. So again, the first time I showed that SED at a Beacon Satellite Symposium, older scientists said, nope, this can't be real. We would have seen it. And we said, oh yeah, I think it's real, but we'll go back. And sure enough, it was repeatable. We saw it every time there was a large KP or a large geomagnetic storm. We saw this feature up the East Coast. And we started making movies. Basically, this is sort of the initial DAISY, but you can see it says Distributed Networks of Sensor Yield Global Physics. Oh, thank you. Unobtainable with single-point measurements. And where's my movie? There it is. And so as you look at the movie, you can see we can start seeing how it's changing and rotating around the world. And that's really getting our first system science. And again, about this time, the image satellite was up there. And we went to a conference, I remember, in Lowell, and John Foster was there. And this is actually looking at the plasmasphere from up above, and it's looking down. And there was a big, probably the biggest storms in the last 20 or 30 years happened in this time frame between October 28th and October 31st. But before, the plasmasphere extends out to many Earth, 6 or 7 Earth radii. Afterwards, they had this tail, and they saw that it was greatly reduced. And they were saying, what is this? What's happening here? And John was quick to say, I think that's what we're seeing on the ground. These two are connected. And sure enough, and I don't actually have the mapping here, but this is from another storm, but it turns out there's a one-to-one mapping between this tail and the storm-enhanced density plume. So we made the first MI connection at that time. Now, in Japan, they started doing comparisons between air glow and air glow emissions over here, and using their many, many receivers to do TID propagation. And again, they confirmed that we were measuring TIDs that were associated with the air glow at the same time. And we've obviously done a lot. Shengrong especially has done a lot of work with TIDs recently, but I'm just showing you that this is in 2017. You can see we get these very, very large structures, large TIDs moving down following a storm. So now another thing we can see very, very carefully with it is our solar flares. Basically, a solar flare is a violent explosion, energy equivalent to 100 million hydrogen bombs go off, and they can arrive in 8 minutes from the sun to the earth. And the duration, it depends, minutes to 3 hours. they impact the daylight side of the Earth. Well, GPS is incredibly sensitive to this. And I'm just showing, this is a big solar flare, but I have evidence of even very small solar flares being picked up by our data. And what you're seeing here, we've looked at just little bins, and every time there's a jump like this, that means receivers are losing lock because the TEC has changed too much from the solar flare. But you can see it's the daylight part of the Earth that really gets affected, and there's this big increase following a solar flare. This actually was discovered by a Cornell student, and he was just looking at receivers, and what you're seeing is basically, I may have to redo this, but there was an increase in the solar radio noise background. So if you're just looking at the background, so you're calculating your noise, all of a sudden that noise level goes up in the L-band frequency. And what that does is it means your signal to noise goes down, and all of those receivers that turn red, they are the IGS receivers. All of a sudden, they're not seeing anything. Anytime they're red, they're gone. So this didn't happen. Basically, it didn't happen over a long amount of time. I think this is only like 10 or 12 minutes. But the important point was nobody anticipated that you would see these radio bursts in the L-band frequency. And Larissa has done a lot of this work basically connecting the forces between the lower atmosphere and the difference between the magnetosphere forcing versus the stratospheric troposphere forcing. And this was, again, probably 10 years ago, and she can certainly confirm that initially people weren't buying it. But basically, I think we've proved that there's a huge effect, and this goes back to the very early days, probably 10 years ago, where we had a stratospheric warming. We didn't think much was going to happen. This is actually the drift as measured at Hickamarka, the temperature, and then after the warming, there's a huge change, a huge uplift in Hickamarka, a large change in the drift, and a large change. So we were really starting to do, I would say, system science with all of our measurements. Now here, luckily, we've done a lot of work with our friends at Virginia Tech, and we are continuing to use their data. This was done by Evan Thomas, and basically we showed that there were additional returns from the SuperDarn radars in the SED plume, and we started doing these correlations. Many of you have used their maps and their convection patterns that we've overlaid onto the TEC. And shown how the TEC tends to propagate over the poles following the convection pattern that is measured by SuperDarn. Oops. So what's in the future and where are we going? Well, I think now it's no longer just GPS. It's more, how can we make it more efficient to combine many, many different types of data? What can we do as a community to really get this to happen? This is from, actually from Calgary, where they're trying to build out many, many different receivers, and green line all-sky imagers, blue line all-sky imagers, an imaging rheometer, a spectrograph, GNSS, and continue to build up the infrastructure. They want to actually do the physics in the cloud so that we can have better real-time understanding of what's happening in these regions. And just to give you an example, but I'll show you more in a minute, here's the aurora. Basically, you see a lot of changes in TIDs here at the same time. So we have a project where we're actually, and this data is partly on Madrigal now, but we're using the combination of what we call the McCAWS network, which is our receivers, that's all of these here, with the chain network, along with our GNSS TEC product and the scintillation parameters combined with the all-sky image data. We're also now trying to pull in SuperDarn into this mix as well. And I'm going to show you where we are. So this, I like this, but here you can see everywhere there's a circle. That's where we're measuring pretty intensive scintillation. And you can see it's overlaid onto the all-sky imager here, and then you can see the TEC underneath it. This one basically is from March 1st, and you'll see this is just one time period at 10 when the storm hits. And I want you to watch over here so you can see the scintillation developing. I think it's still 7. I don't know if I can stop it at 10, but what you can see is we're overlaying it. There's a big substorm, and we have this huge evidence of scintillation going up all through Canada. What I found interesting, I think this is evidence of precipitation, but we see an increase in the TEC right in this region at night following the storm. And we actually see that fairly consistently during a number of storms. This is recent. It's from April 15th, 2022. Here you see all of this TEC, right here, and you see in this region a fair amount of scintillation, and then you're seeing the TIDs right after it. One of the things we're seeing is that if you actually look at finer scales, we're seeing a lot more structure in the TEC, where I'm seeing actually waves of increased TEC in little bitty and very small region, and they seem to correlate with what's happening with the magnetometers. So I think there's a lot to start getting into. Now, this is from Josh Semeter, but basically he's saying we need to look at the ionosphere as an Earth system sensor, not only to look at MI coupling, but also to look at sort of the variations that you're going to see from propagating up from the ground. This is actually from the large earthquake in Japan, but as you know, we've been doing that. Now this is something I want to show you. This is our original, this is Mango data from 2017, so it's an older version. This is our differential TEC product. And you can see there's fairly large structures and the correlation here. But Jonathan Makela has done something to improve the quality of the Mango data, and I just want to show this. Is this gonna, this should be moving. This is a movie. It worked, oh, it did work. And I want you to see how much resolution we're seeing. I'm not sure. Well, there it is. Okay, just trust me. I don't know what happened. Okay, Jonathan. What I want to say is that the granularity of what is now available from Mango has greatly increased, and I think now we're looking at a database that is just begging for more analysis, and I think we need to take advantage of that. All right, we can go back. I'm going to go forward. The main thing I wanted you to see was oh, now it's working. All right. I don't know what happened there, but you can see the winds are changing direction, so the TIDs are moving. I think this is really exciting. Then many of you saw the recent Tonga volcanic eruption and all of the TIDs, and certainly our group has been actively involved. Both Shungrong and IRCHA have papers now published, and I strongly recommend you look at them. This is the GOES imagery. This is Shungrong's. It's just the local, sort of looking directly at it. You're going to see these large waves coming out from the earth, from the volcano, and then you'll see a little bit later. And they lasted for many, many hours, and they changed wavelengths. I don't know how long this goes on. I think I'm gonna end it here because, and this is where I think we're going, and you heard our last speaker mention this, we need to actually start pulling in all of the satellite signals that are available. And that means far more than just GPS. Certainly means starting to incorporate BeiDou and all of the LEOs and every piece of data that we can get, because I think that's where we're going to get new revelations. Now, in our group has started processing BeiDou, and I just want to show you that it's the combination of BeiDou plus GPS that really gives us what we need to analyze this Tonga event. And if you go to the next slide, this is what you get when you combine both data sets. And I want you to see, you can really see the energy propagating away from the center of the eruption. So, big data and computational reconstruction. That's what's going on in the next decade, and I think all of us need to be aware of it. I think you heard from yesterday in his talk that he's merging data now from different sensors. This is ground-based TEC, Spaceborne data sets, GNSS TEC, Cosmic RO, JSON, Millstone incoherent scatter. By combining all of this using an ensemble-based background error covariance approach, three-dimensional variation or a 3D VAR approach, and sparse matrix storage, he was able to produce this incredibly detailed and three-dimensional image of the storm-enhanced density feature over Millstone. And that's the first time we've actually been able to achieve this. And I think that this is where we're going in the future, but you really need to start combining and utilizing all of the different data sets. So it's our job as a facility, I think, to help make that easier for the community, and to try and simplify it so that people aren't spending hours and hours trying to merge the different data sets. And this last one, I like this. That's my daughter, sorry, and my son. And they're both Cornell graduates. And they went to visit North Vietnam, and this is now several years ago. And this 18-year-old Hmong guide had a much fancier cell phone than either Emma or Nate. And I'm just saying that these cell phones now, many of them have GPS in them. Now, I think we're kind of restricted, I think, in the US, but if you go outside of the US, you can really work with these cell phones that are tracking not only GPS, but also GLONASS and BeiDou. And you can start doing science by really grabbing that data and starting to crowdsource it. So this is a large area that I think is still worth exploring. Everybody on this planet has a cell phone almost. I think there's more cell phones, in fact, available than there are people. So communication is going to only increase, and we need to try and take advantage of that. So since this is Texas, and I think I'm about right on time, I want to end. This was actually 15th of September in 2000, but we do see aurora in Texas. I bet you didn't know that. This is a very large geomagnetic storm, and this is in El Paso at the Big Bend National Park. So just remember, even though you think of the aurora as something high latitudes, during big storms, high latitudes can come down even as far as Texas. And remember, I was going to end with a rainbow. Just remember, everything in my career has really been based on stuff I learned pretty early on as a child. So I just want to summarize. It's really important. Oh, I think I made a mistake here, but find easier ways to integrate different signals. We've got to actually do that. And that's the future. We need to utilize all signals, and we need to improve visualization data sets, standardized data formats. We need to collaborate. Modelers, data scientists, experimentalists, all of us have to collaborate. We need to start to make things easier on ourselves and not harder. So that's it.
Awesome, cool. Thank you so much. I'm very happy to see you give this talk. You're like a tour de force in the community, so that was awesome. Thank you so much. Okay, let's go to Slido, and if anyone has any questions in the audience, just raise your hand. But let's start off with, as you know, selective availability was not turned off until May 2000. How do you account for this in your early studies?
Well, as you probably know, back in the very first days, they didn't even have it on. There was no selective availability, and there was no... Selective availability really isn't our problem. It's the other thing which is still going on, and for some reason I can't think of it. Selective availability and where they actually diddle with... There's two things they do, and one of them's still going on, but the receivers take advantage of it. However, prior to 1991, there were no things on, the data was as beautiful and clear as it could be. And then the DoD actually did put on selective availability, which wasn't our problem. It's the other thing. And for the life of me, I can't think of the name of it. But the way we get around it is that the receivers actually correct for it to get it. All of the receivers do.
Very cool.
If that answers.
Makes sense. Anything from the audience? Yes, Andwaki.
This is not a question. Don't worry, Anthea. But when Yen introduced Anthea, he forgot one critical contribution that Anthea did. For this outreach program, the UN sponsor program that we have been doing for the last almost 2 decades now, since 2007. So she has been very, very instrumental. And she mentioned Zambia. That was the first time I took her to Africa. Then she became an African, and she kept asking me to go back again and again and again. So Anthea was very, very instrumental on this outreach program. And I was telling to Phil, travel without Anthea was boring, really.
And I will say Africa is incredible, but...
Very cool. Anything else? Larissa? Oh. Yeah, I'm thinking we could do that, yeah. If there's no other questions, let's all give Anthea another applause.
And we are not done yet. I think first, I wanted to thank Anthea for this incredible trip over decades from 1950s and all the way into the future. But most of all, I think I wanted to compliment and recognize Anthea's not just amazing vision, but it's not just vision, it's a strength and stamina and dedication to implement that vision over the decades, to bring these amazing data sets to this entire community which is now fundamental for all the space physics science that we are doing. Anthea, you are truly true inspiration for all of us. And as a small token of our appreciation to memorize this day, if we can get so that Astrid can take picture. So this is from all of us.
As I said, once again, I'm still I just spilled water. Here, hold this. I'm still amazed I'm here, but don't give up. Everybody, just keep. Sometimes the going does get hard, but I think it does help to have a vision, keep going. And I want everybody to remember science is probably one of the most amazing, fun, great things we can be involved with. Keep it. Don't forget that. Just don't forget it. All right?
Yeah, I just want to do more about that.
All right, that's it.
All right, and we have one. I don't need both of these, but I got them. All right, and we have one more speaker this morning. We have another early career highlight. This is from Leslie Lamarche. I've known her for many years. I can't give like a good enough intro for how highly I think of her. But her talk is going to be Dayside plasma flows and ion heating in the polar cap. Take it away, Leslie.
Hi, everyone. It's, again, an honor to be here. I was a little intimidated to be following Anthea, but we're going to do the best we can and then get on to lunch, or I guess break. Cool, that works. So this talk is on frictional Joule heating in the polar cap. Why do we care about heating? It's a major input of energy into the ionosphere system. When you have heating, it causes outflow, which then mass loads the magnetosphere. Again, this coupling ionosphere-magnetosphere system. I look at it using the Resolute A incoherent scatter radar, which is a incoherent scatter radar in the polar cap, so 82 degrees MLAT. And that makes it kind of ideally located to examine polar cap dynamics and various things that are happening at the extreme high latitudes on open field lines. So this is the radar. It's very large, but it's a really fantastic facility. Like all ISRs, you can measure electron density, velocity, and ion and electron temperature, which makes it kind of perfect for doing heating studies. One of the really nifty things about this radar, as well as some of the other, they're phased array and electronically steerable, so they actually have beam formation that can point in various directions, and we can reorganize them fairly quickly. Which means that there's a great diversity of modes which are useful for examining structures at a wide variety of scales. This is an example I wanted to show, just kind of introduce this concept of ion heating. Let's see. This is ion temperature on this top plot, and you see you have this very substantial enhancement right here. And what you notice is if you compare it with plasma drift velocity, it occurs at the same time as this very substantial enhancement in ion drift velocity, which is what we expect for heating events. You have drift, and it basically causes this kind of heating event. So I wanted to show this example because it's a really cool example that kind of demonstrates this concept and shows the capabilities of the riser facility. However, I would like to point out that this is in no way a normal event. This is one of the most spectacular velocity events we've ever seen with the radar. But we did see it, so it does happen. And you do get strong flows in the polar cap routinely, just not quite that strong routinely. So looking at flows in general, we're looking at, if we want to look at the statistical convection, we can look at the SuperDAR convection maps that kind of say, on a statistical point, what do we see? You have your normal two-cell convection pattern for southward IMF. But when you have northward IMF, what happens, you end up having reconnection happen in the lobe of the ionosphere, which tends to drive these small convection cells, small reverse convection cells on the day side, which can produce some really interesting dynamics in that region. Specifically, if we look at that in comparison with neutral winds. So this is from the HL-TWIM model, which is an empirical model based on high latitude Fabry-Perot and I believe 2 satellite data sets. It specifically looked at collecting high latitude instruments, so it hopefully has a little more fidelity in the high latitude and polar region. You see, you get some very interesting things where you get these kind of complex dynamics there, but then perhaps mostly still anti-sunward neutral flow. And when you start to have opposing ion and neutral flow, that's one of the prime conditions for heating events. So this is just another similar example from a different paper. This is from the cluster, statistical mass from the cluster electron drift instrument. And it's basically looking at different clock angle positions, so kind of greater resolution of what was shown on the previous slide. And yeah, in this Dayside noon sector region, when you have northwards IMF or northwards IMF with some BY component, you do get these very complex convection patterns that are basically a prime situation for shears, for various flow patterns and mixing that could contribute to heating. So we want to look at how common this is on a statistical standpoint using the RISER database. What I did is, I'm looking at the database from 2010 to 2020, so basically a decade, do some filtering to remove data we don't trust, post-integrate all data to 5 minutes, and that's just so we have a uniform data set that we're looking at. We're looking at a vertical profile, so extract the median plasma parameters, so electron density, ion temperature, and electron temperature between 300 and 400. So we're trying to look at just the F region. So we do that for the entire 10 years. We do something very similar to extract the 3D plasma drift velocities, which are derived from the line of sight drift velocities using this Heiselman and Nichols algorithm that was published in 2008. I'm not going to go into detail about exactly what it is, but suffice to say, we do some nifty post-processing to the line of sight velocities and can extract a 3D vector of the drift velocity of the E cross B drift velocity in the polar cap. Neutral and temperature and neutral velocities we're taking from empirical models, and then bin data, both in MLT and IMF clock angle, and average in each bin. And that produces something like this. So you have local time, MLT on the x-axis, clock angle on the y-axis. 0 is northwards IMF, 12 is noon. TI from riser N, TN from the standard MSIS-E neutral model. So you can see with this, and here this plot is just TI. This is kind of relative TI, so you subtract out the neutral temperature. And in both cases, there is a fairly substantial enhancement in the air average temperature in the noon sector under IMF BZ North, which indicates to us that some of the things we were looking at on the previous slide, so when you're looking at that region where you have convection cells, the sunward convection cells and reverse convection cells, you do have substantial heating under those conditions statistically. And then we look at the velocity, because we know velocity is also an important indicator of heating. And here we have, they're a very similar plot. This is the magnitude of the ion velocity. This is the magnitude of the relative ion velocity, so ion velocity minus the neutral velocity from the HL TWIM model. And one thing I'd like to point out at this is, so if the ion velocity and the neutral velocity are moving together, you expect each cell in this plot to be lower than each cell in this plot. And for a lot of this plot, this is true, with a very notable exception, again, this period with northwards IMF and in the noon sector, where you actually see an enhancement here. And this suggests that under those conditions, ion velocity routinely does oppose the neutral velocity when it reverses and starts flowing sunwards. So that kind of gives some more credence to this theory that this is something that happens. It happens routinely, and it's quite possibly a very important factor in energy input into the polar cap and heating in that region. next thing we do is we're actually trying to model a few case studies. Use the ionosphere polar wind model, which is a model developed by my co-author Roger Varney. It's a fairly sophisticated model, solves 8 moment transport equations. How we drive it, or the parameters we use in it. So again, for neutrals, we're going to use NRLM-SIS, HL2M for the neutral winds, and the solar UV spectrum comes from the HUVAC model. Particle precipitation and plasma convection are actually things that we are going to try and drive with empirical models and assimilative models to try and create as realistic of a situation of what the background for those is as we can. Particle precipitation, we use Ovation Prime. It's a statistical model based on, or an empirical model based on DMSP particle energy data. You get energy flux and total number flux, which is what we need to input into the model. And this is a fairly common model. It's used for a lot of things. It is statistical, so it can't represent sudden changes in some of the dynamics that you usually see in the auroral zone. But it's what we used for this case, and it was allowed us to put some input that we believe was somewhat realistic based on the conditions into IPWM. And then for convection, we use super darn convection maps, which again are very classic data product used by many, many people in this field. This is just an example, another one of these convection maps where you have the reverse convection cells in the Dayside and sunward flow. Super darn, I believe it's been talked about a lot, even just today. High latitude, network of high latitude HF ionospheric radars. Line of sight velocities, when they take them all together with all the different radars, that allows them to create these really useful convection maps that map the entire process. And then wind backscatter is not there, so these are all backscatter regions. It does default to a statistical pattern based on the historic super darn data set. And these are the results from that IPWM run. So this is the potential, and you can see we were looking at a particular northward period. You do have your reverse convection cell, which comes from the super darn data, precipitation from Ovation Prime, and then this is the output. So this is ion temperature that we get out of the model. You can see right here, that is an ion temperature enhancement that correlates quite well with this reverse convection cell. So qualitatively, at least, you see IPWM reproducing heating that we'd expect from this particular convection pattern in these conditions. However, when we go and compare that with the riser data, what we did is we took the one cell from IPWM that riser was underneath, and we plot it against the riser altitude, high elevation beam altitude. And you can see that this is the period we were looking at. Yeah, you have heating, but nowhere near as much as you see in riser. So even with those as realistic inputs as we put from global drivers, we're still not reproducing this degree of heating that we see in the riser data. To dig into that a little bit more, we're going to look at this ion energy equation. So this expression is a reasonable approximation. It's not perfect, but it's reasonable for the ion energy equation in the F region. And the significant thing about it is you can see that your ion temperature is directly related to the ion, the VI-VN difference. Just kind of go back to the very beginning of this talk and those two statistical charts we were showing. So what we're going to do is examine the importance of mesoscale flows, which may not be captured in the SuperDARN data, just because it is a global network, by comparing the TI calculated using the velocity from these global convection patterns with TI calculated using velocity from riser, which is a much, much more local measurement, and see how they compare to the measured TI from riser. And then this is the result of that. So this plot, these top two panels of velocity, red is SuperDARN, blue is riser. And you can see for the V north component, they agree fairly well. For the V east component, there is a substantial flow seen in the riser data that's not being captured by the convection maps. And when you do that calculation, which is the equation on this previous slide, the dark blue line is that calculation using the riser velocity. The dark red line is that calculation using the convection Mach velocity. And then the light blue line is actual measured TI from riser. And the pink line here is the TI from IPWM. And what you can see is the two blue lines. So this is the riser, this is riser ion temperatures measured directly, and ion temperatures calculated using that ion energy equation approximation based on riser velocities. They actually follow very closely in this region. And so that's saying that if you take into account the higher velocities here, you can reproduce the high heating you see and the temperature enhancements you see very well. For the other case, however, the calculation based on the convection map follows the IPWM calculation very well. So what that's telling us, and IPWM has a much more sophisticated technique for calculating ion temperature than the equation on the previous slide. But that's really highlighting the real importance of effectively looking at these mesoscale flows, and when there are very fast flows, even if they're very localized, they're very significant for heating the ionosphere. So in conclusion, we see ion heating frequently, especially in the new sector under IMF North. If you're looking at global convection maps, these are fantastic, and they do reproduce a huge amount of dynamics that we see on a global scale, but there do seem to be cases of localized flows that produce significant heating locally that, kind of by definition, things at that scale are not usually captured by convection maps. So in the future, some of the things we'd like to do to continue on this work is, I know there are better methods. So the SuperDarn community has made huge strides in creating very high-resolution maps. So starting to look at those and see how much, if we look at higher and higher resolution of those at the global scale, if we can start to replicate some of those dynamics. An additional more examination of neutral winds, if we can actually take measurements from FPIs, which are a little challenging on the polar cap because it's day a lot of times, and as well as small-scale precipitation features that are not necessarily captured, nor do we expect them to be in global statistical models. So, is there any questions? Or?
It's day a lot of the time. I love that. Any questions? Chungran.
Very, very nice work. Thanks very much. So in very beginning, probably very early part of your talk, you show a slide. And the bottom panel is the ion velocity, and the other one is the ion temperature. Not the earlier ones, maybe the introduction part. Yeah, this one, yes. So I noticed that the ion temperature enhancement was more significant below 200 kilometers. Is this expected behavior or unexpected? I mean, the higher enhancement, low altitudes than higher altitudes.
Usually we expect the ion enhancement, especially in these data, to follow wherever the electron temperature or the electron density is the highest, just because that's where the peak F region is. The F region can move between 200 to 400 kilometers, depending on the time. So this is 2014. I wouldn't say it's unexpected, but yeah, the altitude dependence is definitely something to keep in mind in terms of where these enhancements are taking place. I believe we do usually see them at the F region peak, wherever that happens to be.
And we have another one?
Very nice work, Leslie. I'm just, and this is a good slide, the same kind of time around 19. I get a little worried about non-Maxwellian plasmas in there. Did you guys take a look at the spectra in there, and just to make sure that you're not misinterpreting some of the ion temperature as being a sort of non-thermal plasma?
So we did not, but the non-thermal plasma, I believe this calculation actually, it ends up being a lower limit of what the temperature could be. And we can maybe talk about that, but If anything, it's worse. Yeah, and this is an exceptional event. This is a fun event that Riser observed, but it's not normal.
And one last quick question.
Hi, I'm doing the middle and low latitude electrodynamics, and I have a question about this slide. So on this slide, we can see the plasma drift velocity around, I would say, more than 2,000 meters per second. And when you derive this heating, does any assumption about supersonic or should be subsonic in the fluid?
I'm actually not sure about that. This, again, this event is highly unusual. It's a fun example of the magnitude of exactly what kind of crazy things can happen when you get open field lines being dragged across the polar cap at crazy velocities. Yeah, I'm actually not sure about supersonic. We should talk about that. That's an interesting point.
All right, that's all the time we have. Thank you so much, Leslie. And that basically concludes our morning plenary. So get some coffee and get ready for the next bunch of talks.